So let's start illustrating the method of maximum likelihood with an example dealing with a Poisson distribution. Say we're quality control engineers at Kruger Industrial Smoothing, and we occasionally produce defective bearings. In fact, we have reason to believe that the count of defective bearings produced in a week follows a Poisson distribution, but we're not sure what the rate of occurrence would be. Say we collect the number of defective bearings in two particular week-long periods and found 10 and 12 defective bearings, in these two different samples. And we'd like to figure out what the rate of defective units per week is based on this sample, albeit it's a small sample, but this is just for illustrative purposes. So first let's think about what the probability function is for a Poisson distribution. So let's say we have random variable y that's, well, let's just write it out. We have random variable y that measures the count of defective bearings in a week. The probability that y takes on a particular value, little y, you might remember, is lambda to the y, e to the minus lambda, divided by y factorial. That is the probability function for a Poisson distribution. And we saw two particular realizations of this random variable. We saw 10 and we saw 12 in a sample of size 2. So what we're wanting to do here is we're wanting to collect a sample and then determine what this lambda would optimally be. What's the value of lambda that optimizes the likelihood that we pulled those two samples from this distribution? So what would our likelihood function be? Our likelihood function for y1 and y2, we had two observations, and we have one parameter, lambda. That's just the probability of y1 multiplied by the probability of y2. We had just two, this is y1, y2 factorial. We just had two observations, so we're going to remember the likelihood function multiplies the PDF together. This is not a PDF because this is a discrete distribution, but the idea is the same. We're multiplying the probability of one times the probability of the other. That gives us the likelihood function for these two observations. So let's put in those particular values of y1 and y2. They were 10 and 12. So we have lambda to the 10, e to the minus lambda over 10 factorial, multiplied by lambda to the 12, e to the minus lambda over 12 factorial. We can multiply those through together. Lambda to the 10, lambda to the 12. We just add those together. That's lambda to the 22. E to the minus lambda times e to the minus lambda is e to the minus 2 lambda. And down here we've got 10 factorial times 12 factorial. So this is the likelihood function for those two observations, 10 and 12. So what do we want to do here? First, let's take the natural log. So let's rewrite this likelihood function. Let's rewrite this likelihood function like this, to just make it a little more easy to look at. It's lambda to the 22, e to the minus 2 lambda, times 10 factorial, 12 factorial, to the negative 1. So we've got three things multiplied together. This is the equivalent of this right here. So if we wanted to take the natural log of this, take the natural log of both sides, that is the natural log of lambda to the 22 plus the natural log of e to the minus 2 lambda plus the natural log of 10 factorial, 12 factorial to the negative 1. So we don't have a lot of time to recap the natural log function, but I will just tell you that the natural log of lambda to the 22 is 22 natural log of lambda. The natural log of e to the minus 2 lambda, the natural log and the e are inverse functions. They cancel each other out. So that is just negative 2 lambda. And the natural log of 10 factorial, 12 factorial to the negative 1 is minus 1. okay, we've got that minus 1 out front, times the natural log of 10 factorial, 12 factorial. Okay? So this is the natural log likelihood. Okay, and what we want to do is take the derivative of the natural log likelihood with respect to lambda. Okay? So the derivative of the natural log likelihood with respect to lambda is the natural log of 22 times the the derivative of this, which is the derivative of 22 times the natural log of lambda. Okay, the derivative of a natural log is 1 over whatever is inside the natural log. Okay, so this would be 22 over lambda. The derivative of this is 22 over lambda. The derivative with respect to lambda of negative 2y is negative 2. The derivative with respect to lambda of the natural log of 10 factorial and 12 factorial is just 0. Okay? Because there's no lambda in here. Taking the derivative with respect to lambda of this just constant is 0. Okay? So our derivative here of the natural log likelihood is 22 over lambda minus 2. We set that equal to 0 and solve for lambda. That would give us the lambda that maximizes the likelihood function. Okay? So we put this on one side. Ultimately, what we get is lambda is equal to 22 over 2, which is 11. Okay? So what's the optimal value of lambda that maximizes the likelihood that we would have collected a sample of size 10, a sample that included 10 and 12. Okay? Two samples, 10 and 12. What's the value of lambda that would maximize the likelihood that we pick those two samples? It's 11 defects per week. Okay, so this is us working out the method of maximum likelihood for a particular small example of a Poisson distribution. And so 11 is the maximum likelihood estimate based on that sample of size 2.